I'm a professor of physics at the University of Surrey, and the ideas and theories of the great European scientists like Galileo, Newton and Einstein lie at the heart of my work. But there's another side to me. I'm half Iraqi, and I'm keen to investigate stories I'd heard as a schoolboy in Baghdad of great astronomers from the medieval Islamic world whose work shaped the discoveries of these later Western scientists. So I'm going on a journey through Syria and Egypt to the remote mountains in northern Iran to discover how the work of these Islamic astronomers had dramatic and far-reaching consequences. First crucial step in a journey that led to modern physics. Well, I agree, but it does seem a bit odd that one doesn't hear much about where Copernicus got his ideas and information. The impression is that they came out of nowhere.
The beginning?
And the beginning is all in Arabic.
It certainly is a real revelation to me that he explicitly mentions a 9th century Muslim for providing him with a great deal of observational data, an astronomer who lived in Damascus called Battani. Like all the great scientists of the Islamic Empire, Battani lived in a culture without portraiture. All we have are later impressions of what he might have looked like. Copernicus, in fact, made extensive use of Battani's observations of the positions of planets, the sun, the moon and stars. He worked with Latin translations, similar to this one, of the Syrian astronomers' data.
Kitab al-Zij al-Sabi. So this is Battani's Zij, his book of star charts. So it has the Arabic...
Yes, all the Arabic treatise, yes, and then the Latin version.
That's convenient.
But he certainly had the data, the observational data by Battani.
Their estimate of the year was 365 days, 6 hours and just over 10 minutes. To improve on this, Battani used his ingenuity and a device like this, an armillary sphere. He used it to measure how the length of shadows varied over the course of a year. With this information, he was able to work out the precise day on which it's both light and dark for exactly the same time, the so-called equinox. And he repeated his measurements over the course of 40 years. Now, here's the clever bit. He examined a Greek text that was written 700 years earlier and discovered the precise day on which its author had also measured the equinox. He now had two vital pieces of data: the number of days between the two observations and the number of years. He divided the first number by the second to arrive at an astonishing result. A year is 365 days, 5 hours, 46 minutes and 24 seconds.
And he gets the new number, which was only 2 minutes of the modern observations.
2 minutes?
2 minutes
so
of only.
The length of a year to an accuracy of just 2 minutes.
Exactly, the one he calculated.
What's astonishing about the accuracy of Battani's measurements is that he had no telescope. He used an armillary arm, his naked eye, and devices like this, an astrolabe.